Perfect. And we are streaming. Hello, everybody. We're going to get started in just a second. We're going to just give it a couple minutes for people to trickle in. Okay, it is 12 Eastern, so I think we will go ahead and get started. Hello, and welcome to an introduction to Qiskit, presented by IBM. We are really thrilled to be collaborating with IBM over the course of this hackathon. They have designed a really exciting challenge for the 24-hour hack this weekend, and this tutorial is just designed to get you up to speed on their platform Qiskit so that we can be ready to start solving some exciting problems. In just a second, I'll hand it over to James and Eliza so we can get started, and then afterwards, we'll do a brief Q&A. If during the course of the tutorial you have any questions, please post them in the Twitch chat. We'll try to answer them as they come up, and we'll bring some of the questions up at the end. Without further ado, it is our pleasure to introduce James and Eliza. James Weaver is a developer, author, and speaker with a passion for quantum computing. He's a Java champion and a Java 1 rock star. James has written books including Inside Java, Beginning J2EE, the Pro Java FX series, and Java with Raspberry Pi. As an IBM quantum developer advocate, James speaks internationally about quantum computing with Qiskit at quantum and classical computing conferences. He tweets as @JavaFXpert and blogs at javafxpert.com and culturedear.com.
Eliza is a PhD student at ETH Zurich and working part-time for the Qiskit team, helping with outreach activities and developing educational material. In her free time, she loves to dance acrobatic rock and roll.
Please join us in welcoming James and Eliza.
Hi, hi everyone. Thanks a lot for the nice introduction. So yeah, my name is Elisa Bäumer, and in the call we also have James Weaver. James Weaver will be working mostly from behind the scenes now, so he will be the one in the chat answering most of your questions in the live chat, and then also in the end moderating. So let me give you an outline of the talk today. So I will start with repeating the most important quantum computing concepts. I know you had an introduction yesterday, so I hope you are, at least those of you who don't have a quantum computing background yet, already got to learn quite some basics. But then I just repeat the most important things, give you a very short summary. Then we will all run our very first circuits using the IBM Quantum Composer. And afterwards, I will actually show you one algorithm, robust algorithm, which is a more advanced algorithm that we can then run using the IBM Quantum Lab. And in the end, I will show you a bit of our work in the IBM Quantum Community team, how you can learn more about quantum computing, about all our educational material, as well as our outreach activities. So yeah, let me start by giving you repeating the most important concepts of quantum computing, in my opinion. So the first one is superposition. I probably have heard of that before, but yeah, so I guess most of you are actually computer scientists, so you all know that classical states, if we compute with them, they're all either 0 or 1, while in quantum mechanics, we can actually be in what we call a superposition. So we can be simultaneously in state 0 and in state 1, which then means that we can perform calculations on many states at the same time. So if you assume, for example, on a classical computer, you have 3 bits, then we can, with those 3 bits, implement one number one out of 8 numbers. While if we now have quantum computers, we can be in a superposition of all those 8 numbers at the same time and compute with all of them at the same time. Which then leads us to some quantum algorithms where we get an exponential speedup, which sounds really cool, right? However, there's a very big but that we really have to emphasize, because once we measure our superposition state, it collapses into one of its eigenstates, which means that if I do a calculation on all of my states, and then I do let's say all those 8 states, and I get results to all of them, then in the end, I only get one of the results. I don't get all 8 of them. So it is not that easy to design quantum algorithms. However, there's something that we can make use of, which is what we call interference effects. So maybe you've heard of that word interference before when you in physics, maybe in a class where you learned about the double slit experiment with light waves. So we can have constructive interference where amplitudes add up to each other, and then we have a higher amplitude in the end, or destructive interference where they cancel each other out. And this is an effect that we can also make use of when designing quantum algorithms, so that we can have, for example, if we design a quantum algorithm that is looking for one specific element, that is like a search algorithm, then we can use these interference effects such that all the elements that we're not looking for cancel each other out. And then we have constructive interference on the element that we're actually looking for. And this has a very high chance in the end to be measured then. So the second concept that I want to talk about is entanglement. And I will now show you a very, very high level explanation of that, a very macroscopic description. So assume we have Alice and Bob, as always, and they have 2 dice that are entangled. So at some point in the past, they met and they entangled these 2 dice. Then Alice flew to the moon while Bob stayed on Earth. And now they make a measurement. So they roll the dice. And Bob, let's say Bob got a 6. Then if they had a maximally entangled state where they are maximally correlated, then he would know immediately that Alice will also measure a 6. So the measurement of Bob immediately influences the measurement of Alice, and Bob immediately knows what Alice is going to measure, even before she measures it or looks at it. However, this is now a very macroscopic example, and this is something that is not feasible at all. We cannot entangle dice. We can entangle things like photons or ions, but we cannot entangle dice. Also, it is maybe not a very good example. I just wanted to give those of you who have never heard of entanglement a very rough idea of what it is and a very high-level idea of what it is. But it kind of makes you maybe believe that all kind of strong correlations immediately imply entanglement, which is not the case. You could, for example, classically think about the case where, let's say I have a black card and a red card, and I mix them very well so that I don't know which one is which. and then I give one of them to James. Now I fly to the moon and I look at my card once I'm there. The moment I look at my card, I know immediately what card James has. So if my card is red, I know immediately that James' card is black, or the other way around. So this is also some correlation, and it's also a strong correlation, and immediately I know which card James has, but this is not entanglement. This is a macroscopic description, and this has nothing to do with quantum entanglement. But so yeah, that's why also the dice is maybe not that good, definitely not an accurate description of entanglement, but just to give you an idea, entanglement is some very strong form of correlation, but it's a form of correlation that we don't have in our classical world. So that's something that is new to you, something that you haven't seen before, basically. And so yeah, the last concept that I want to quickly go through with you before showing you Qiskit code is the quantum gates. So as you maybe remember from your quantum mechanics class, quantum theory is always unitary. And if you don't remember that, or if you never had a quantum mechanics class, just believe me that this holds, which means then that all quantum gates always must be represented by unitary matrices, which are matrices where we have U dagger, when U dagger is the complex conjugated and transposed of a matrix, times U must be identity. So that's a mathematical way of describing what kind of gates we can have. But let me give you some examples, maybe the most important examples for now. So the first one is what we call the bit flip gate, or also the NOT gate. It is given by the Pauli matrix sigma x. And if I apply, the reason why it's called bit flip gate is because if I apply to the state 0, it changes it to 1. And if I apply to 1, it changes the state to 0, which is also why we can call it the NOT gate, because it is the quantum equivalent to a classical NOT gate, where we just change the bit. However, given by this matrix, it is unitary, and we could also apply it to superposition states. Then the next example is what we call a Hadamard gate. I think it's really one of the most important gates because I think pretty much any algorithm I know starts by applying Hadamard gates. The reason it's so important is because if I apply the Hadamard gate to the state 0, then I'm getting an equal superposition of 0 and 1. So I get the state 0 plus 1. And then we have this factor square root of 2, which is just for normalization. And if I apply to state 1, I actually also get a superposition of 0 and 1. However, I get a minus sign in between. I get 0 minus 1, which is what we call a phase, a relative phase between the two states 0 and 1. And this is what then leads to the interference effects that I talked about before, that we can have to cancel out some states that we don't want and amplify those that we want. And the last gate that I want to show you is what we call a C0 gate. And the reason it's called a C0 is because C0 is short form for controlled knot. So we have a controlled qubit. In this case, it's the first qubit. And then we have the target qubit, which is the second one. And so in the case where the control qubit is 0, we do not do anything on the target qubit. So applied to 0, 0, we get 0, 0. If we apply C0 to 0, 1, we just get 0, 1 because we're not doing anything. By the way, this is also, since we have 2 qubits, our matrix has to be 4 times 4 dimensional. If, however, now the control qubit is in state 1, then we apply a NOT gate. So we flip the second bit. So if I start with 1, 0, 0, then I get 1, 1 because I flip the second bit, or qubit in this case. And if I apply to 1, 1, I get 1, 0 because I'm again flipping the second qubit. And the way we would write it as a quantum circuit, for quantum circuit, we always have these lines that go from left to right time-wise. So we start in state X and on the first qubit, and in state Y on the second qubit. And now this small dot here that represents the control. So we control on the qubit that is in state X. And then we have a NOT gate that we apply to qubit Y, but conditioned on the controlled. And then what we get is the control qubit actually never changes. When you look here at the first qubit, nothing happens. So whatever is the input will also be the output. However, for the second qubit, we can see only in the case where the first one is 1, we actually change the second one, which means that for the output that we actually get is X plus Y modulo 2. which is why we can also call why it is basically the reversible XOR gate, because the XOR gate is the one in classical computing where we have X and Y and we output X plus Y modulo 2. And the reason but the problem with, in general, with an XOR gate would be that if I just output X plus Y and I tell you this is 1, then we don't know whether X was 0 and Y was 1 or the other way around. So it's not reversible. However, since we now output also X, you can actually construct what the input was and it's reversible. So this is a quantum gate. It's also a unitary gate, as it has to be. And it is used to create entanglement because we get some correlation here within the output, which you will see later. Good. Now, this was all that I wanted to very quickly recap on quantum principles. Now I'm going to show you how we can use the quantum composer. So you may all want to go to quantum-computing.ibm.com, or those of you who want to interactively join and create your very first quantum circuits if you haven't done so yet. So let me share my side as well. So I'm at quantum-computing.ibm. Yeah, sorry. Sorry, apparently automatically the stream went on. Sorry for that. So, okay, now I hope it works. I'm at here. You can see the link quantum-computing.ibm.com. And now I want to open if you're new to that site, if you haven't been here before, you might want to create an account. It should take less than a minute. So I actually give you this 1 minute now. And then we launch the composer. So once you manage to get to that site, just click on Launch Composer. And I do a new file now. And then this is what you should see. If you don't want to do it live, you can just watch my screen and see what I'm doing. Yeah. So as you can see here, we have 3 different qubits, Q0, Q1 to Q2. If I want, I could also add more qubits like this, or I can just easily remove them again. For now, I think 3 qubits are good. The 3 lines. And then we have here C3, which are 3 classical bits. And these classical bits are used to store our measurement outcomes. So we can perform our quantum circuit here, drag and drop some gates, and then in the end do a measurement, and then our measurement outcomes will be stored in this classical register. Okay, so let me start with the first gate. Let's start with a NOT gate, the one that I've showed you first. What you can see down here is the probabilities. So you see in this case now where I've applied the NOT gate, we have 100% probability to measure the outcome 001. Now it's like binary numbers that the last one corresponds to qubit 0, and then qubit 1 in the middle, qubit 2 in the front. So here you actually have, we would now have, as we apply the NOT gate here, or maybe, okay, sorry, maybe I should mention in the very beginning, all qubits are always in the 0 state. So the initialization is always we have all qubits in the 0 state, and now I've applied a NOT gate here. So now the first qubit 0, went to state 1, and we will measure, if we would do a measurement now, we would measure 001. Not so surprising. So let's apply another gate. By the way, now you see it's going back to 000. Okay, if we apply the Hadamard gate, then we're in equal superposition of 0 and 1, which means we have probability 1/2 to measure either 000 or 001, because qubit 1 and 2 will still stay in the 0 state. Now we can get another Hadamard gate here. And now we're in a superposition on both qubits. So both can be either in 0 or 1. So we get in total 4 different states. You can see the first one will always be, or the last qubit will always be in 0, but the others will have all the 4 mixtures, each with probability 25%. And if I do an equal superposition on all 3 qubits, then now it's updating. Then it will be 1/8 on all these states. Okay, now I hope it's gonna update soon. Otherwise, I'll just explain with this one. So what you can see on the right-hand side here is the Q-sphere. The Q-sphere is a way to illustrate how the quantum state looks like. I don't have time to go into detail on explaining that, but what you can see here is that we have 4 different states because we're still in the superposition of those 4 states. It didn't update. But yeah, so that's why we have 4 different states and there's no phase between them right now. So they're all blue. If I would apply some phase gates in between, then these would change the color. Now it updated. Now we can see we have 8 different states because we have applied a Hadamard gate to all of them. That's what I mentioned at the beginning. We're in equal superposition on all 8 states. And here you see all these 8 states. And let's say I might get a phase gate here. So these are just changing the phases. Now we don't have plus everywhere, but we have some complex numbers. And now here we have different, you can see in the Q-sphere, we have different colors, but still exactly the same 8 states. Okay, but now these states were all still, we did not correlate any of the qubits yet, so we couldn't do anything useful. But what we want to do is I want to show you how we can correlate them and get some entanglement in there. For that, I need the CNOT gate, that I explained to you before. And I first bring the first qubit in a superposition. And now I'm applying 2 CNOT gates to the other qubits. And thereby I entangle them. And I bring them to a state. The state is actually 0, 0, 0 plus 1, 1, 1. So instead of having 8 different possibilities, now I only have 2 different possibilities. And the moment I measure one of the qubits and I measure, for example, 1 on the second qubit, I immediately know that both of my other qubits will also be in the 1 state. This is what I tried to describe earlier with the dice, where we know immediately that the state of the other qubits. So let's see what happens when we run it. So if we would just want to run it, I can click here in the right corner on Setup and Run. And let's choose first simulator. So we're choosing the IBM QASM simulator. And I can click on Run. And now it tells me here, circuit needs at least 1 measure. So, okay, that was, of course, now I put the circuit, but I told you before, we have the classical register to store the measurements. And on the quantum computer, on the qubits, once they collapse, we need to somehow store the measurements. So I will add the measurements here. Good, and then we can run it again. And maybe something that you can see in the meantime while it's running is now that I added the measurements, my probabilities actually switch to not being 50-50 anymore, but 100% on 1-1-1. That is because now for this simulation of the probabilities, the measurement is included. And I told you once we measure, it collapses to one of them. So now we have, it just went to 1-1-1 with 50% chance, which is here given by the seed. So I can change this. If I change the seed, you see now, then it might swap to the other state and maybe back, but maybe it stays there. Also the Q-sphere changes accordingly. So we just have some seed and then it gives us the probability. But let's see, let's have a look at the result of that we just did, this one. So here we can see our output of the circuit that we just ran. As we run it on the simulator, we have no noise. So the chance to measure each output was exactly 50%. However, what we see here is, well, it is basically 50-50, but there are more zeros than ones. You can see the number is not exactly the same, but it's slightly different. But this is not due to noise, as I said, but it is because, well, if I give you a coin and I ask you to flip it 100 times, then even if it's fair and we have a 50% chance of measuring each output, you will most likely not measure exactly 50 times head and 50 times tail, but there is some Gaussian curve that describes how it gives you the outputs. Okay, I told you in the beginning, we all want to run our very first quantum circuit on a quantum computer. So now I use the simulator, and let's see how good our quantum computer is performing. So I reset the filter here, and I just go for the computer that has the least number of jobs in the queue, which is for me now the Mumbai device. I think for you it might be differently because, well, I have access to a few more quantum computers than you have, but you should still see a lot of different devices there that you could use. But you might also be a bit longer in the queue now. So if I click here on this left side onto composer jobs, that's where you can see your jobs. And now I'm waiting for, now we can see here, it's still pending. It's in the queue and expected to run in a few seconds. Yeah, I might actually just show you one from earlier, otherwise. Oh, we just go back to that in a few minutes. So for you, it might anyway, you can send it now and then check in a few minutes or a few hours or whenever you feel like it, or tomorrow, and then still see your results and look at them. And they might be in the queue for a while, especially if now a lot of us are trying to run circuits, then it might take a while. But yeah, so I can actually no. Okay, let me go back then to the presentation. Or before I'll show you here some Qiskit code. So here on the right side, you can see the code, how it looks like if we program it with Qiskit. Because now we use the quantum composer, which is where you can drag and drop some circuits and some gates, some gates and some measurements and all of that. But in general, you might want to do more complicated, more sophisticated circuits. You might want to have some loops and some conditions and some other gates than just those that are up here. So then you want to use the quantum lab, which we'll also do in a few minutes. And there you need to, well, first import, of course, your registers, do some imports. And then you can see here how you would actually run whatever we just did, this circuit with Qiskit. So you would first build a quantum register with 3 qubits, then the classical register with 3 classical bits to store the results and combine them to a quantum circuit. And now here you see the gates that we have applied. We've applied, it's just circuit.h to apply the Hadamard gate, .cx, where we always need to specify, of course, which qubits we're using. Here we were using qubit 0, then qubit 0 and qubit 1, 1 and 2, and then just the 3 measurements. And that's it already. That's quite straightforward to program that. And in the meantime now, we completed the measurement of the circuit. So let me show you the results of the actual measurement that we did. Here we go. As you can see, as expected, we have almost half probability to measure 0, 0, 0, and almost probability 50% to measure 1, 1, 1. However, there's also some noise here. As you can see, there's also some with some small probabilities. We also measure one of the other outcomes, which ideally we shouldn't measure, but well, there's always some noise. And what you might also notice is that the probability to measure 1, 1, 1 is smaller than all zeros, which is because of the coherence times of the qubits. So after some time, they go from the excited state to the ground state. This is more likely to happen than the other way around. That's why instead of 1, 1, 1, we also have bigger probabilities here at 2 states being in 1 and 1 being in 0. So 1, 1, 0, 0, 1, 1, and 1, 0, 1. Well, there's a small probability, but still, you can see this is more likely to happen, and the 0 state rather stays at 50%. But yeah, let's go back to the presentation. I hope you can see the presentation. Yeah. So I've showed you now how you can use the quantum composer, but I also want to show you, as I just mentioned, how to do more advanced circuits with big quantum lab. And what I want to show you actually an example is Grover's algorithm, which was developed in 1996. And so I'll just give you a short overview of how Grover's algorithm works before we can then implement it with Qiskit. Actually, I will implement it with Qiskit and you can watch my slides because that would take too long to do it interactively. So Grover's algorithm is an algorithm that solves an unstructured search problem. For example, one could think of searching an unsorted database with n elements, where n is 2 to the number small, 2 to the small n, because you always look at bit strings. An example that is often made is a phone book, which I think is very nice to think of it, but I will tell you later why it's actually not such a good example. But for now, you can think of, I give you a phone book, and instead of giving you a name and asking you for the phone number, because in that way it's sorted, I do the opposite, and I give you a phone number and ask you what is the name corresponding to that phone number. Well, in this case, on average, you would need to go through n/2 names to find the right answer. And the classical computer cannot do that any faster. However, a quantum computer can actually do that in √n time. So especially if I have a lot of names or very big database, if my n is very large, then this gives me a big advantage. And by the way, now I made this example with a phone book, but I will later on show you other examples that are more suitable. And so just to give you a very rough idea of what the quantum algorithm does is it uses what we call amplitude amplification, which consists basically of 3 steps. So you have the quantum circuit here. We all start in the 0 state with all qubits. Then we apply a Hadamard gate. As I told you, all quantum circuit, almost all algorithms start with applying a Hadamard gate to all qubits, which brings us to the equal superposition. Then we apply what we call a phase oracle, which changes the phase of the marked elements of the element that we're looking for. This is step 2. And then step 3 is what we call a diffuser, which performs in the end a reflection around the average amplitude. And so we have these 3 steps. And then step 2 and step 3, we actually need to repeat r times, where r depends on the number of elements that we have. And in the end, I apply measurement on all qubits, and with a very large probability, I will measure get as outcome the element that I was looking for, the marked element. So this principle of amplitude amplification, I want to show you here in some graphs. So in the beginning, we start, as I said, with all qubits in state 0, and here I put, well, instead of putting the binary numbers, we have here the decimal numbers. So we're in the state 0 with amplitude 1. Now we apply the Hadamard gate to all qubits, which brings us to an equal superposition of all n elements. The phase, but now notice that I'm plotting the amplitude and not the probability. The probability is the amplitude squared. So, and the amplitude can actually also be negative or could have, in theory, any complex phase. In the beginning, if I apply Hadamard gates, there is no phase between the different, so it's just +1 between all the elements. So they all are 1/√n. Now if I square that, I would get 1/n probability for each of the n elements, which is what we want. Good. Then the second step is where I apply my phase oracle, which flips the sign of the winning element W. So this is my winning element. Then it flips the sign from, so instead of having amplitude 1/√n, we get amplitude -1/√n. If I would apply a measurement now, it wouldn't make a difference because if I square it, the minus sign anyway disappears. Also, it's, by the way, the absolute value squared. So it wouldn't help if I apply phase I or something. But so then I have the third step, and the third step is a reflection around the average amplitude. And since I flipped the sign of my winning element, the average amplitude actually decreased a bit. So if I now perform a reflection around it, all elements except for the winning one will decrease a bit in the amplitude, while the winning element will be boosted up here and will have a quite high probability now to be measured. But, well, not high enough yet maybe, so we can apply step 2 and 3 a couple of times. until at some point we will reach something like that. So usually we cannot reach exactly 0 for the other elements, but we can reach something that goes exponentially close to 0. And then we have almost 1 for the winning element. Okay, so let me show you how this now gets implemented with Qiskit. So first of all, I need to make a lot of imports. I'm doing them here, just importing some standard stuff. And then I define my two oracle, first my oracle, the face oracle, the one that gives a minus sign to the marked element. Don't worry about it too much. You will just see that as face oracle in the circuit. Then we have the diffuser, the one that that reflects around the average amplitude. And then I put them all in a function called rover, where I create a quantum circuit with my n qubits and n bits. And then I determine how many times I need to repeat it, r times. And I just first put them all into equal superposition with the Hadamard gates. And then I add the phase oracle and diffuser r times in total. In the end, I measure all of them and give back my quantum circuit. So let me show you how the quantum circuit looks like in 5 qubits. So here I'm choosing x as a random number, that is the marked element. In this case, the marked element would be element 26. And I have 4 rounds of applying step 2 and 3. So first step is here, the Hadamard gates, and then 2, 3, 2, 3, and so on, the oracle and the diffuser. And in the end, I measure all of my elements. Now, let's see if we use the simulator, how the histogram looks like if I actually run this circuit. And well, here we see we have a 99.9% chance to measure this element, which is the binary representation of 26, which was our marked element. And what we can see though is that there's really, from the histogram, we couldn't even really tell. But here, if we output the number of counts, we can see out of those 10,000 counts that we did, 9,993 were the one that we wanted. And then we have 1 count for each of the other few elements. But I think it's pretty clear which our marked element was. Now you might wonder what happens if we would not apply step 2 and 3 that many times, but if we just do step 1, step 2, step 3, and then a measurement. And so if we would do that, then we would end up in this distribution, which already also identifies our marked element. You can see here, this is the marked element. Great, we can already identify it. However, we only have a 25% chance to actually measure it. So if I would only do 1 shot, I would only get 25% to measure the right result, while I have a quite high probability to measure something else. So I better repeat steps 2 and 3 a couple of times to get a higher result. You can see here, the more we do, so the blue distribution is what we get with 1 round. Then if we have 2 repetitions, we get the pink one, with 3, the purple one, and with 4 repetitions, we get the orange one, which is basically 100%. And okay, this was now the simulator, but let's see how good this actually works on an actual quantum computer. Now the problem is with too many qubits, it does not work too well, honestly, but we can decrease our number of qubits to 3. And also now I'm choosing not only 1 marked element, but I'm choosing 2 random marked elements. As backend, I choose the least busy backend, and let's run it. And so now we see here, randomly, I get states 2 and 7 marked. And I submit a job to, here this thing pops up now, IBM Q jobs, where I should very soon see what, here you can see now my job. It shows the IBM Q Lima device, but now it's going to be in the queue for a bit. So I actually ran it before. So we can see how noisy it looks. For example, here when I ran it some time ago on the Vigo device. Here you could see in this case, the marked elements were actually the elements 1 and 2. And you can identify them. However, you have, of course, much more noise than if you would do it on the simulator. You're not close to 100%, but you're only at 30% each. So, but at least you can already identify what the marked elements are. Okay. Now, the last thing that I want to show you on using Qiskit is I mentioned before that the phone book is not a good idea of for using Grover. The phone book is basically I'm looking for one specific element. But that's also what I did just before. I marked one element and then I looked for this element. But you might have noticed that now in the way I needed to construct my oracle, the oracle actually needs to know which element I marked. So in the case of a phone book, I would need to tell the oracle which one is the right answer. But in order to figure that out, I mean, either I already know the answer, then I don't need the oracle, I don't need quantum circuit at all, or I would need to feed the oracle in advance all possible inputs. So I'll give the oracle all phone numbers and all names. But then just feeding the oracle with all that information, in the meantime, I could have just used the classical algorithm to look for whatever name I'm looking for. So this is not efficient. What one might use Grover's algorithm what it might be rather useful for though, is if we have what we call satisfiability problems. So satisfiability problems are problems where I give you some conditions, and if these conditions are also, and then we have an oracle or some function that can easily check whether all conditions are satisfied. An example would be an example would be Sudoku. So if I give you a Sudoku, if it's not filled out yet, it's hard to find a solution. But if I give you just some solution, or maybe not solution, so it's just some Sudoku field that is filled out with numbers, you can easily check whether it's a valid solution or not. So that goes much faster to check whether it's correct or not. And another example is what I will show you here. So first I do some imports again. But now the example that I wanted to show you is of a satisfiability problem. As imagine that you throw a birthday party and you have 5 friends that you want to invite, that you could potentially invite: Alice, Bob, Charlie, Dave, and Eve. But then you have a few restrictions that need to be all satisfied in order to have a nice birthday party. So the first restriction is that Alice and Eve are always fighting, so you definitely do not want to invite both of them. The second point is that Alice and Charlie are married, so if you invite one of them, you also have to invite the other one. The third one is that you don't want your party to be boring, so you want to invite at least one of your entertaining friends, Bob and Dave. And so Bob or Dave, or at least one of them. Then you also notice, though, that if you have Bob, Charlie, and Dave together, then the party might get out of control. So you definitely shouldn't invite all 3 of them. The fifth condition is that if you know that if you invite Bob, he will not have any idea about birthday presents, and he will definitely ask Alice. So if you invite Bob, you should also invite Alice, though not necessarily the other way around. And then the last condition is that you know that Dave will anyway only come if Bob comes, so there's no point inviting him if Bob is not getting invited. So yeah, this would be an example of a satisfiability problem, and the question is, whom can I possibly invite now? And this is something that we could solve with Grover's algorithm by using all these statements and converting them into what you call 3-set problems. So, for example, the first one, Alice and Eve are fighting, we cannot invite both of them, means that we cannot have Alice and Eve. This is a logical statement. And if we want to write it as a clause that we can use for our 3-set problem, we can rewrite this as not Alice or not Eve. This is the statement number 1. Now with Qiskit, if I want to put that into my Grover's algorithm, I assign all my parties, Alice, Bob, Charlie, and so on, ABC. I encode them as 1, 2, 3, 4, 5. So not Alice or not Eve would be -1 for the minus comes from the not, and -5, and then a 0 we always put in the end. So the clauses, we could rewrite them like that, all of them, all the conditions. And then we can input that into a 3-set problem and run it on our Oracle. So now this is much more complicated, of course. So I imported from Aqua, from Qiskit Aqua, I imported some Grover functions that are predefined that I didn't need to write myself. And now I can run it and see what the answer is. And the answer is that we can see here, this is the answer, 1, 2, 3, -4, -5. That means Alice, Bob, and Charlie I can invite, but not Dave and not Eve. And we see, okay, actually we would only get this with probability 1/4 approximately, but still this is the solution, and we can check, yes, if we check all our conditions, we can see that this is indeed a valid solution, and actually the only valid solution to all our restrictions. Now this was run on we used here the simulator, here the custom simulator. We did not run it on actual device. And the reason we didn't run that on an actual device, I can show you here. If I would compile, look at the compiled circuit, I can see that this circuit has a depth of 239. So depth is the number of time steps, basically the number of gates we need to apply. More than just the number of gates, but the number of time steps in which we can apply gates. And this is just too much for the current state, for our current quantum computers. They could not handle that. We would just get too much noise in the end. So for now, we need to stick to our simulators, but hopefully in a couple of years, this is something that could be run on a quantum computer, and then of course also more complicated problems, because this one you might have solved by yourself in the meantime. Okay, that was everything I wanted to say about Qiskit, and now about the implementation. But now let me talk about our IBM Quantum Community team and what we can offer and what our mission is. So of course we want to target researchers and turn them into users, but we also want to educate students. So we have a lot of educational material that I will present to you soon. And then also developers, we really want to get more and more developers that maybe by now only look at classical computers. We want to engage them and motivate them to use quantum computers as well. And then also anyone else who's just enthusiastic about quantum computing. We want to raise even more awareness about our quantum systems and get them excited, even more excited about quantum computing and how to use them. So we have basically 3 different pillars. We have education, where we put a lot of effort in, a lot of outreach activities, and community building events as well. So to go a bit more into detail, if you're wondering, if you want to learn more about either Qiskit or just also quantum computing in general, I could highly recommend the Qiskit textbook, where we start with the very basics of quantum computing and a bit of the introduction that I gave basically now. So learn what quantum bits are and what basic gates are, but they also bring you to state of the art of quantum computing applications. And you can always directly implement things with Qiskit. So you have always buttons that immediately show you how to implement the things that you've just learned, like some basic quantum algorithms, how to implement them directly with Qiskit. You can open them in the website that I just showed you. If you're not so much into reading and you prefer to either listen or watch instead to learn, then I can highly recommend to you the Qiskit YouTube channel, where we have Coding with Qiskit seasons. We have our 1-minute Qiskit. If the Coding with Qiskit is too long, we have the 1 minute, which is like a 1-minute summary of different features of Qiskit. We also have the seminar series, and we have the Superposition podcast. Then another thing, if you really want to dive very deep and detailed into specific topics of quantum computing, I can recommend to you the Qiskit, our lectures from the Qiskit Global Summer School last year, which was a 2 weeks intense course that had in total 20 hours of lectures. And we have all these lectures are now available on YouTube, so you can just find them, well, if you follow this link. you can just see all of them and hopefully learn a lot. But if you're not really so much into learning too many details, but you just want to have some fun while learning more about quantum, I can then recommend to you the quantum games that we have. We have a quantum board game, which is called Entanglion. It's a 2-player board game where you learn a bit about different superposition states and entangled states. Then we have an app called Hello Quantum, where even kids can try to solve some small puzzles that, well, you can see here, that also work with gates. And we have Qiskit blocks, which is basically like, it's a game that you can play on the computer. It's like Minecraft. You can walk around with quantum circuits, solve some riddles as well. And yeah, it was actually, if you have more questions on that, you should ask James, because he's the one who built that, and who, yeah, he did a really good job. I can highly recommend you trying that out. And if you're already quite familiar with quantum computing and you want to have some more challenges, so you may have heard of our quantum challenges that we had so far. We had one last year in May, and then we had another one last fall, where we had different exercises that started easy and got more and more difficult. You can see here the knowledge, how it increased by the people that actually did them. And well, I can of course highly recommend those. I think it's a very fun way to get more, to try out new problems and try to solve them. And if you're interested in that, stay tuned for our next one, which is coming soon. And the other thing that we have running, which is also more targeting researchers and people that are already quite familiar with quantum computing, is the Open Science Prize. Here you can actually, in total, we have a prize of $100K US. There's 2 research level challenges. One is about reducing gate errors, and the other one is about increasing circuit fidelity for graph state preparation. It's only running for, I think, 10 more days. So if you're excited about that, hurry up. But otherwise, I'm sure there's going to be more things coming up soon. And the last thing that I want to mention is actually how I got into IBM Quantum, into the team, is via a Qiskit camp. We had these university hackathons and Qiskit camps. We had them in the US, in Europe, in Asia, and Africa so far. Unfortunately, right now, due to COVID, it's of course not possible to have any, but I really hope that in the near future, we will again be able to host these fun events where you get to meet a lot of, like 100 other really enthusiastic people that you build teams with them, and you have a quantum hackathon and try to work together on projects. And I think it's a very fun way to learn more about quantum computing. And yeah, with this, I would like to thank you for your attention. And I'm happy to answer questions if James did not manage to answer all of them yet. Of course, that would also be great. But yeah, let's see if there's any more questions. I guess I stop screen sharing now.
Yes, thank you so much for this wonderful presentation. I know I learned a lot, and I hope that our audience really did as well. Yeah, we can look for some questions through the chat. For all of our participants, if you have any burning questions, now is a really good time to put them in. Let's see. I think a lot of these were already answered in the chat, but it might be helpful just like so that everybody can kind of understand, to just go over them again. One question earlier on was kind of like what sources can cause decoherence when you were going over the implementation of one of the early circuits on an actual quantum computer?
So, I mean, in general, I guess not only any kind of noise, there's a lot of different factors. I mean, first of all, our quantum computers run at like 15 millikelvin. So if there's like small fluctuations in temperature, this can of course increase noise, but then also our qubits, they're not that stable. They have a small coherence time. So after a while, they will just decohere. Yeah, I mean, I'm honestly not an experimentalist. I'm a theorist, so I cannot really give too much explanations about that. But yeah, also there is a lot of noise can come from applying gates, because we apply some, if you apply some lasers or something, then you get noise through that as well, and also through the measurement. The measurement itself, is also quite noisy. So there's a lot of factors where noise comes in. But I'm not an experimentalist, so I hope yeah, it's enough.
Definitely. Let's see, we have a couple questions coming in now. One person is asking, can you explain the Q sphere again? And does it reduce the block sphere for 1 qubit?
No, it does not. So introducing the Q sphere would probably take too much time now. I can just like give a very rough explanation maybe. So every point on the, you have all these, you have different circles on the, sorry, I don't, those lines that go, sorry, like that. And they all correspond to a number of qubits that are in 0 or 1. So we have at the North Pole, we have the state, for example, for 3 qubits at the North Pole, we would have the state 0, 0, 0. At the bottom, we would have 1, 1, 1. Then we have one circle where we have 0, 0, 1, 0, 1, 0, and 1, 0, 0. So all states that have 1, 1, and 2 zeros. And below we have the opposite. And then you can see wherever the probability that to measure a specific state is is given by the size of the blob that you have. So you could see if you know the state that we're in, there will be one big blob at that specific state. If, however, we have like a 50-50 chance, we will have 50% to be in one point and 50% to be in the other point. And then the color of the points indicates the phase, the relative phase between the different qubits. So whether I have 0 plus 1 or 0 minus 1 will have a different color. So yeah, it's different it's actually very different to the blob sphere. So even if I look at 1 qubit, I would just have one qubit, one potential blob at the top and one at the bottom. Maybe if I'm in if I know the state, then it's just one of them. Otherwise, be in a superposition, and then the size indicates how likely it is to measure that state. Sorry, might be confusing, but yeah, I can recommend otherwise to, maybe we can give more detailed answers on Discord or give you more resources there.
Totally. Let's see, I think we have a couple people here asking about some kind of like practical quantum applications and algorithms. One question was like, have you seen any interesting like practical applications built at previous hackathons that really like kind of stand out to you particularly?
Well, I guess the question is what is practical? I mean, I think it's clear that right now we cannot like this quantum supremacy where we can actually do things much better with where we can implement things that we couldn't implement on a classical computer. We're not there yet. Hopefully soon, but not there yet. So of course, also on hackathons that go like one or 2 days or something, people cannot come up with, well, huge projects, right? But there have been, of course, a lot of cool projects. I think maybe James or someone else can post the link somewhere where we have a summary of previous projects. I think they're available online. We can put them maybe in the Discord channel otherwise. So there have been, for example, educating projects, of course, but then also projects that just implemented specific functions that are very useful for researchers or for, yeah, that are part of bigger functions that were needed as well. And yeah, so this is mostly what the kind of projects I think that were done.
Definitely, definitely. I think we have time for a couple questions. Just going back through the chat. Looks like we had a couple questions kind of about the marked element in the Grover's algorithm. I believe one person asked, what happens in the case when the search element, the marked element, is not present in the database? And somebody else asked, what happens if there is more than one instance of the marked element in the database?
So if we have no marked element in there, then it wouldn't work. If we have multiple marked elements, it works actually very similar. The only thing that changes is basically the number of rounds that you need to apply it. So I showed during the talk how it looks like if we apply 1 round or 2 rounds or 3 rounds or 4 rounds, and we get a higher and higher probability. This changes if we have multiple marked elements. So if we, assuming that, I guess from what I understood from the questions, if we wouldn't know that we have multiple marked elements, then we might just have a smaller probability in the end to measure the correct element or one of the correct elements. However, if on the other hand, I know that I don't know the number of marked elements, then I can just use it, then I can do it in a smart way that I increase the number. I assume there would be one marked element, then I do 1 round or 2 rounds or 3 rounds. I just increase the number of marked elements that there could be potentially, and I increase them exponentially. And so in this way, I can actually have a very high chance in the end to still succeed. So it still works is the short answer, sorry. It still works, just might take a tiny bit longer if I don't know how many marked elements there are.
Sure, I think we have time for one more question. Okay, somebody just asked, what is the best quantum volume that any of the IBM quantum computers have demonstrated?
Right now it is 128. You can actually see that if you log into IBM, to the IBM Quantum Composer or Quantum Lab, you can see all devices and you can see their quantum volumes. You might not be able to access all of them, but you can still see the quantum volumes.
Very cool, very cool. A very big thank you to you and James for putting together this amazing presentation and for answering all of the questions in the Twitch chat as well. It's been really, really informative. And for everybody who's watching this, who came on late, this is being recorded and it will be accessible afterwards in the Quantum Coalition Twitch channel. Thank you so much for coming, and Eliza and James, thank you so much for presenting. Look out for the IBM challenge this Saturday, and thank you so much again.
Sure. Yeah, it was a pleasure. Thank you. And thanks again also, Jim, for being in the background and answering all the questions.
Yes. See you guys later.